In this video, we will talk about some important concepts and terminology related to hypothesis testing. After watching the video, you should be able to state the parameter of interest in a study, state null and alternative hypotheses using both words and symbols, identify sample statistics, describe how to use simulation to test hypotheses about proportions, determine whether there is evidence to reject a hypothesis, and explain the meaning of a p-value in context. Throughout the video, we will refer to the dolphin study that's discussed in Chapter 1 of Introduction to Statistical Investigations by Tintel and his co-authors. In this study, two dolphins, Doris and Buzz, had to communicate in order for Doris to tell Buzz which button to push when a light was shining or blinking. Incredibly, the dolphins were able to communicate correctly in 15 out of 16 attempts. In this study, the 16 attempts by Doris and Buzz would be referred to as a sample. A sample is a subset of individuals or outcomes of interest. A statistic is a numerical summary of the sample. In this case, since Doris and Buzz got 15 of the attempts right out of 16 tries, our statistic would be the proportion 15 out of 16. In situations where the statistic is a proportion, we denote it using the symbol p hat. A parameter is the long-run numerical property of a process or a population. In reality, we're not really interested in just the 16 attempts that Doris and Buzz tried, but we would want to know if this experiment had been repeated many times in the long run, how often would they be able to choose the correct button? The long-run proportion of correct choices would be the parameter of interest in this study. When the parameter is a proportion, we denote it using the Greek letter pi. We said that there were two possible explanations for what was happening here. Either the dolphins were just getting lucky and choosing the right button by chance, or there was something more going on. In statistical hypothesis testing, we refer to the chance alone explanation as the null hypothesis. In our situation, the null hypothesis would be that Buzz was not really getting any useful information from Doris, but was rather just guessing. Or another way of saying that is that pi, the long-run proportion of times that Buzz would get this right, is exactly 0.5. The alternative hypothesis is that Buzz was doing more than randomly guessing. We'd like to think that Buzz was getting information from Doris. In that situation, pi, the success probability, would be greater than 0.5. In class, we looked at simulating the null distribution first by flipping coins and then by using the applet on the Rossmann Chance website. We could also do a simulation in R, and this slide shows some code that could be used to do that. At this time in the course, I won't ask you to write the simulation, but the code is available in case you want to look at it later on. The null distribution refers to the set of simulated values of the statistic under the assumption that the null hypothesis is true. We saw the simulated version of this distribution in class based on our simulated values. Here, I've done 10,000 simulations of sets of flipping a coin 16 times and recording the number of heads. We see that most commonly we get 8 heads. Sometimes we get 10 or more, or 5 or fewer. It's very unlikely that we would have gotten 15 or more heads when we flipped a coin 16 times. Graphing that line at 15 shows that it's way off to the right, not consistent with the general values that we were getting by flipping the coin. In fact, in 10,000 simulations, we obtained 15 or more heads only 3 times. This tells us that the probability of the dolphins getting 15 or more attempts right, if they're purely guessing, is about 3 in 10,000, which is very low. We call this proportion the p-value. The p-value represents the probability of obtaining a statistic as extreme or more extreme than the one in our study if the null hypothesis is true. The smaller the p-value, the stronger the evidence against the null hypothesis. In this situation, we have strong evidence that the dolphins were not purely guessing. You may wonder how small must the p-value be to determine that we have strong evidence against the null hypothesis. Depending on the p-value, we get different assessments of the strength of evidence. If the p-value is greater than 0.10, there's really not much evidence against the null hypothesis at all. It's plausible, and it would be plausible in this situation that the dolphins were merely guessing. A p-value between 0.05 and 0.1 provides moderate evidence against the null hypothesis. A p-value between 0.01 and 0.05 provides strong evidence against the null hypothesis. And a p-value less than 0.01, as we saw here, provides very strong evidence against the null hypothesis. We call a result statistically significant if it is not likely to have occurred by chance alone. We've looked at hypothesis testing through what the textbook refers to as the 3S strategy. We observed a statistic from our sample. The dolphins pressed the correct button 15 out of 16 times. We then simulated a situation where the dolphins were purely guessing, where the null hypothesis, the by chance alone theory, was true. And then we looked at where our statistic fell compared to the results from our simulation. Because we got a statistic as extreme as the result from Buzz in the study, only 3 out of 10,000 times, we have strong evidence that Buzz was not purely guessing. As a final note about the study on Doris and Buzz, subsequent studies have shown that dolphins are highly intelligent and that they are able to communicate at a very high level. In the slides is a link to a National Geographic article on the topic of dolphin communication. As a result of watching this video, you should be able to state the parameter of interest in a study, state the null and alternative hypotheses using both words and symbols, identify sample statistics, describe how to use simulation to test hypotheses about proportions, determine whether there is evidence to reject a hypothesis, and explain the meaning of a p-value in context.